In this video, we're going to discuss producing a magnetic field by having current flowing in a wire. So any wire that has current flowing in it makes a magnetic field around it. And the magnitude of this magnetic field is given by the permeability of free space, which is 4 pi 10 to the minus 7 Tesla per meter per amp, times the magnitude of the current. Makes sense. The higher the magnitude of the current, the higher the magnitude of the magnetic field. And this is divided by 2 pi, and also divided by the either r or d, depending on how you want to consider it, which is the distance to that wire. And it makes sense that the farther away from the wire, the less the magnetic field. So kind of as the distance goes away from the wire, there's an inverse relationship to the magnitude of the magnetic field, which makes sense. So not only does it have magnitude, it has a directionality, and the directionality is determined using what's called the right-hand rule. It's very confusing because typically this is brought up right at the same kind of time we talk about the cross product right-hand rule, which is a totally different right-hand rule. In that one, the fingers are the input and the thumb is the output. In this case, the thumb is the input and the curled fingers is the output. So it's totally opposite. So you need to be clear when you're talking about right-hand rule what you're talking about. So we're talking about in this one, for this one, you put your thumb goes in the direction, whatever at that position, wherever the current and the wire is going. So the positive direction of the current, your thumb's gonna point in that direction. And then you use your right hand, and the way you wrap your fingers around is the directionality of the magnetic field. And so here from like a top view, if I had current coming out, I had my thumb coming out, and I'm using my right hand to wrap around, which means the magnetic field has this directionality. It's often drawn as a circle, but really it means is like here from the top view that the magnetic field at any point can be determined there. So again, here's the top view, and this time I have the current coming out, and so when I put my thumb in the direction of the current, then I can wrap around, and that's the direction of the magnetic field. But the magnetic field is really the magnetic field typically you would consider at any point. And then as it gets farther away, then that magnitude of that magnetic field is dropping. And same thing here, as it gets farther away, that magnetic field is in this direction, but it would be less magnitude. And if I had a case where it's from the top view, let's say the current was going in, okay, so then I would have my thumb in the direction of the current, using my right hand spin around, so now my magnetic field term spin around in this direction for that one. Thumb is my input now, the right hand spinning, that's the direction of the magnetic field. That's the directionality, always encircles the wire, and here's its magnitude. So again, here's a side view of this case with the current flowing down. So I'll put my thumb in the direction of the current, wrap my right hand around. You can see on this side it's coming out of the board, and if I spin around, and this side is going in. This side, put my thumb in the direction of the current, right hand spin around. This side the right side, it's going into the board. On the left side, coming out of the board. Okay, so there's kind of the rules on the directionality and the magnitudes of a magnetic field induced by this current which is flowing in the wire. So I have a quick problem here to see if you understand it. So in this case I have a wire that's coming straight out of the board, has a current level I in it. This one has a wire going straight into the board. We're looking at the top view, and it has a current level 2 in it. And I have a bunch of little points in here, like you kind of to draw what's the directionality of the magnetic field. And then problem number 2, this time I have both current 1 and current 2 are out of the board, and at these positions kind of draw the magnitude and the direction of the magnetic field. So you pause the video and solve that. So starting for the first type, we can realize that this problem, we can calculate the component of the magnetic field independently for each one of these, and then vectorially add them. So we can find out, for example, at a position here, we can use our right-hand rule. First of all, magnitude. Magnitude is always this. So permeability of free space over 2 pi times what's the magnitude in the current of this wire containing I1, and what's the distance that point is away. Okay, so that's its magnitude. And the directionality, right-hand rule, says I is out of the board, using right-hand rule. Put the thumb is in the input in this case, spin around. So there's my directionality, which is going to be perpendicular to my distance to that point. So if I think about this point right here, there's my distance to that point. Its right-hand rule says the magnetic field from caused by 1, so B1. And now, since we did the vector component from this current, wire with current, let's consider this one. But this one, again, we'll have to consider the distance now. Instead of totally ignore this one, just think about that. And the result is the summation of the two. This one's in the board, so put my thumb in the direction of the board, and so my magnetic field generated from this one will be encircling this wire in this direction, and then its magnitude depends its distance and what's the magnitude of that current. So I'll draw that now. Now that I've considered the magnetic field from the current flowing into the wire, so put my thumb in here in the direction of the current flowing in, so the magnetic field is going to be spinning around this way around I2. So here at this point it's down, and it's then it's coming around here. It's going to be up, 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 and then it's coming vectorially perpendicular to this distance. So consider this point. There's my distance R2 from it, and since I'm going to use my right-hand rule, this one, I'm going to have my beta 2 component vectorially pointing this direction. So at any point, the magnitude of the magnetic field is the vectorial sum of these. And so you can see for this condition, where the orientation here in between them, so this this 2 made a magnetic field this direction, 1 coming out also made a magnetic field, so going up in the positive y direction. So these are vectorially summing, and since they're right between them, just in the y direction. Here on the outside, the beta 1 was up and the beta 2 was down. Just the opposite here, the beta 2 was up and the beta 1 was down. So this one, because from this one is the beta 2 here, and from this one the beta 1 was down. And then here you just have to do the vectorial sum for the magnitude. And then at any point you just use these two formulas and determine the x and the y components, or whatever. If it's 3-dimensional, you have to consider 3-dimensional, and then you have to do the vectorial sum of them, considering the summation in each of the 3 vectorial directions. So now let's consider that one. Now for the second problem, this time both the currents are flowing out of the board. So the magnetic field around I1, which was from the B1, is always going to be in from top view this counterclockwise direction. So down here, then up and up, and getting smaller magnitudes going farther away. So for example, if this is my R1, there's my distance, and so it's perpendicular. That's my beta 1. It's always this formula to determine its vectorial magnitude, its magnitude, and then its direction, which must be considered vectorial. This time, I2 is also coming up in the top view. So put your direction and your thumb in the direction of the current flow, which is out of the board. Right-hand rule, spin around. So the beta 2s are going to be the magnetic field generated by the current 1 is going to be in this direction. It's obviously bigger the closer it is, the less the distance I2 is. So for example, if that's R2, then the beta 2, the magnetic field caused by 2, is in this direction, and the sum is the vectorial sum of those two. So the net sum would be somewhere in this direction, depending on the distance and the magnitudes of these currents. And you can see in this case now, in the middle, kind of the vectors are subtracting from each other, and on the outsides they're adding together, and here the directions there. So how the problem changes by whether they're the same direction the wire, the current flow, or the opposite direction of the current flow.